Thank you. Thank you. If people in the back can hear me, let me know. I'll try to be as loud as possible for everybody. Thank you all for joining us tonight. We'll talk about what I think is probably one of the most important and amazing discoveries in history of astronomy. That is the direct detection of gravitational waves. So, to begin our journey, we have to travel back in time to the year of 1915. Back in 1915 was the year when we first took a photograph of Pluto. 1915, also we're in the middle of World War I, so the world is on fire. But so is the mind of one German scientist. That scientist's name is Albert Einstein. See, in 1915, Albert Einstein published his theory of general relativity. Up until today, this is still the most complete mathematical understanding of how gravity works. Up until 1915, gravity was this force. We understood how it made objects behave, but why exactly was happening was poorly understood. It was this like mysterious force acting on a distance. So Einstein came around, and first he said, guys, this thing you call space, and this thing you call time, they are two different faces of the same coin called spacetime. In fact, this thing called spacetime is a fabric that perpetuates all across the universe. This spacetime has a funny geometry. It gets curved at certain places. And depending on how the spacetime gets curved, that determines how objects move in the universe. To understand more about his theory, let's look at his Einstein's equation. Not E equals mc squared, something a bit more complicated, but don't worry, you don't need either Latin or Greek to understand this. All you need to know is that the left side here this tells us everything about the curvature of spacetime, about this geometry, while the right side tells us everything about how everything else, such as mass, energy, how everything else moves and acts. And basically, Einstein showed that everything in the universe is intrinsically interlinked with the geometry of spacetime. And there's two ways we can read this equation. We can read it from right to left. And if we read it from right to left, we see that everything in the universe, mass and energy, affects how the spacetime gets curved. So a very good analogy of spacetime, if we think so spacetime is this three-dimensional monster in space plus a time dimension. But if we just think of it in 2 dimensions, we can think of it as a trampoline. And if you take a trampoline and you put a bowling ball in the middle of a trampoline, that bowling ball would bend the trampoline around it. And if you throw a small tennis ball around it, that ball would get attracted by the bigger one, simply because of the curvature of the trampoline. Similarly, the sun, just like a big ball, is bending this fabric of spacetime around itself. And in this way, it's creating gravity. It's pulling things toward itself. So one thing is things bend spacetime. You can also see it the other way around. That is, the way the spacetime is curved affects how things move in space. So, for example, when the Earth rotates around the sun, it is the same way as you actually will observe in the experiment we'll show you later on, as if you had a heavy ball, a bowling ball, on a trampoline that bends the trampoline, and the small ball rotates around it. Also, not only mass gets affected this way, but so does light. For example, if we had a star that is hidden behind the sun, and we were over here on the bottom, as the light moves towards the sun, instead of going this way and hitting somewhere there, because the light would encounter this curvature of space-time, it would actually bend its path and it would bend towards us. So effectively, we will be able to see stars that are supposed to be behind the sun. We will actually observe them a little bit on the side. So during the day, unfortunately, the sun is very bright, so we wouldn't be able to see these stars. However, during a solar eclipse, when the moon hides the sun, if this effect is true, then during a solar eclipse, we should be able to observe these stars on the side. And in fact, in 1919, an astronomer by the name of Eddington went out, and there was a solar eclipse, and that's exactly what he did. And what he observed was that the stars that were supposed to be behind the sun were actually being observed on the sky right beside it. So that was one of the first tests of general relativity. In science, we need to test our theories before being certain that they're true. That is, a theory has to give a prediction, and that prediction has to come true afterwards. Another such prediction is something we call the Mercury's perihelion precession. Perihelion is a fancy word for saying the closest distance an object gets to the sun. So planets, they orbit around the sun in not perfectly circular paths, in somewhat slightly elliptical. So sometimes over the year, sometimes they get closer, sometimes they get farther. And using the physics before Einstein, we're able to predict how this distance that Mercury, that any other planet besides Mercury, we're able to predict this distance of closest approach. Mercury, however, we weren't able to predict it, and we weren't sure why. But then Einstein came around, and with his general relativity, was able to explain it. In fact, his mathematics were able to predict exactly where Mercury would be during the year. And why is that Mercury has this weird anomaly that other planets don't? That Mercury is much closer than the rest of the solar system to the bending of the curvature of space-time by the sun. Another test is also something called gravitational lensing, which you will see here on the top right corner, where we have a simulation of a black hole and a galaxy moving right behind it. So as you can see, what is happening is a very similar effect to when light gets bent by the sun. In a similar fashion, the light from the galaxy gets bent by the curvature in space-time that this black hole is making. And in fact, it's lensing out the galaxy behind it in this weird, deformed way. And there are many other tests for GR, and we could spend the entire AstroTour on it, but I would like to just skip forward to the most important one for tonight. That is the prediction of gravitational waves. In 1916, Einstein and another mathematician called Schwarzschild, they looked at the mathematics and they said, wait a second, if we had two massive and compact objects, for example, that just like in this animation, they were spinning around each other. Those two compact massive objects, they would be able to deform this fabric of space-time that we talk about. But these deformations, these waves that it would create, would be very, very tiny. So for a while, there was actually people weren't really sure whether that was not like a mathematical fluke or was it real. But by the 50s, people came to a consensus that yes, gravitational waves should exist if GR is true. However, they're very weak and probably really impossible to detect. So what objects can deform so extremely the fabric of space-time? Well, these objects have to be very massive and very compact. Because remember, when we talk about the bowling ball example, the heavier and the more compact the mass is, the more it's going to deform space-time. Such objects are, for example, neutron stars that are pictured here. And a neutron star is basically if you take our sun and you start squishing it, and you squish it to diameter of as big as Toronto. You would have squished it so much, you would have broken all the atomic bonds inside of it. So you'll have this sea of neutrons. And it will still have the mass of the sun, but it will be very compacted. Another such object that would do that thing is black holes. Black holes are if you take the sun and you squish it, you squish it even smaller than Toronto, you squish it to a diameter of 1, 2, 3 kilometers, you would have bent space-time so much that not even light could escape from this hole that you would have created in space-time. So black holes and neutron stars rotating around each other could create such events. And here we have a numerical simulation done by a graduate student from our department, Sergei Osokin. In it, you see two black holes rotating around each other. And as they do so, they perturb space-time. And they create these waves that are emitted from them. The color scheme, the wider the wave is, the higher its energy is, the amplitude. So as you can see, the more they spin around each other, the more energetic these waves become. And if we just see it again. So these waves, gravitational waves, they have some energy. Energy has to come from somewhere. So this energy comes from the orbits of the black holes. As the black holes orbit around each other, and as they create these gravitational waves, they dissipate some of the energy from their orbit into these gravitational waves. And as they lose their orbital energy, they're getting closer and closer and closer to each other in such a way that at the end, they will merge into one singular black hole. And you will notice that at the end, as the waves become more and more energetic, there is a huge burst of gravitational waves that occurs at the end. And it is this burst that people who look for gravitational waves are looking for. All right. So we know what objects would create gravitational waves. But what do gravitational waves look like? We know waves in everyday life. We know water waves, the disturbances of water. We know sound waves. We may not see them, but we can hear them. So sound wave is basically the air getting compressed, and there's disturbance in the air that your ear can detect afterwards, and your brain can understand it as sound, as noise. So how does gravitational waves work then? Because there's nothing in space to be bent, it bends space itself. So if a gravitational wave was moving away from the board right now, you would see that space would get stretched here and compressed in this direction. Then it would be stretched in this direction and compressed in this direction. And you're going to have this constant stretching and compressing. And you would ask yourself, if we're getting bombarded by gravitational waves, maybe, all the time, wouldn't we die from this all constant and stretching of space around us? You would think so, but the stretching and spacing is actually very, 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 very tiny. How tiny it is, if I was holding a 4-kilometer meter stick here, and a gravitational wave passed by me, To detect the difference, I would have to be able to resolve 1,000th of the diameter of a proton. And the diameter of a proton is so small, it's like 0 point followed by, I think, 15 zeros afterwards, meters. And how small it is? Well, this is, for example, to show you how small it is, this is a video of the hydrogen atom. The hydrogen atom is made of an electron and a proton inside. And we'll zoom in inside towards the proton, and then you will notice at some point we're going to be hit by a gravitational wave. Yeah, that's it. So if I had a 4-kilometer long stick, that's how good of a microscope I need to have to be able to see the gravitational wave. So gravitational waves are very, very, very weak. So before the announcement of LIGO, many people, and I'll admit it, including me, were kind of skeptical about it. So I'll tell you a small anecdote with my friend Nick, who is here on the left. Nick, he works in our department. He studies actually merging of black holes. So this is exactly his territory. And he loves LIGO. His cat is named LIGO. So on February 10th, he came to me and said, well, aren't you excited about this announcement tomorrow? Do you think that LIGO would have detected gravitational waves? To which I said, no. You see, I was really skeptic, but you know, to be fair, gravitational waves are so weak, we probably don't have the technology for that. And even if by some miracle we did have the technology, they're very quick. So when you saw that those two black holes merging together, the event that we were supposed to detect was that last bit of a second at the end. They're very quick, and once they pass through you, they don't happen again. So if you've missed it once, you've missed it forever. So, which is why I told him that it's like looking for a needle in a haystack if that needle lasted only a fraction for a second. In fact, I was so sure of myself, I said that if by some miracle LIGO detects something, so here I am. On February 11th, I was woken up around 10 a.m. and I'll give you a dirty little secret of graduate students' life. We tend to work until 2, 3 a.m. We have very bad habits. And wake up at 10, 11 a.m. Don't do that, but we do it. So around 10 a.m., I wake up, my phone is buzzing, Twitter, hashtag Einstein was right is trending. LIGO is saying that 100 years after Einstein's prediction, we detected a gravitational wave emitted from binary black hole merger. Followed by the astro community, articles, politicians. This thing went viral really, really quickly. So a question to ask ourselves at this point is, how did LIGO do it? If these things are so hard to detect, how did LIGO do it? Well, he did it by creating the most precise ruler ever. At this point, let me step back a little bit and explain what LIGO is. LIGO is this huge scientific collaboration of many scientists throughout the world. It's an acronym. It stands for Laser Interferometer Gravitational Wave Observatory. And it's basically shaped as an L. And here we have a bird's eye view of one of them. There actually are 2 such observatories in the United States, one in Washington and one in Louisiana. So how did LIGO detect these waves? Well, it's in the name. It's an interferometer, which means it's measuring interference of light. And interference is something you notice in everyday life. If you throw rocks, stones in a lake, you would notice they would create this wave pattern. And when different waves meet together, sometimes they would become almost invisible. Sometimes they would get amplified. Another example is if you have two speakers and you walk, they both have the same music. Sometimes there are some locations in the room where the sound is more weaker, somewhere where it's much stronger, and that's due to interference between the waves. And to understand it, here on the bottom left, we have two waves, and the bottom is the sum of those two waves. And whenever those two waves meet, and a peak meets a peak, and a trough meets a trough, the sum of those two waves becomes amplified, becomes much stronger. However, if a trough meets a peak, suddenly the signal disappears. It's called a destructive interference, because basically you're summing up two waves that self-destroy each other at the end. So that's how LIGO exploits this amazing principle in nature to our advantage. So it has, here we have a somewhat simplified diagram of what the real instrument is. So that big L that you saw were those, where's the laser? All right. Those two arms over here. So what LIGO does is it shoots a laser, and then if those arms, it shoots a laser, the laser gets split in two parts, then each hits a mirror and then gets reflected back, gets recombined here, and gets projected at the detector. Now, if those two arms are perfectly at the right angle, and if they are the exact same length, we expect when those waves come back to see a destructive interference. That is, to see absolutely nothing at the detector. However, if by some miracle, that miracle being a gravitational wave bending space, one of those arms changes in length, then one of those signals would have traveled a bit more than the other one. So peaks wouldn't meet troughs anymore, so we wouldn't have a destructive interference anymore. We would actually see a signal. And I have a small video here to show that exact same principle. What you will see a laser being shot from here, the light being deflected towards these two mirrors, and then when the light gets recombined here, you will see at first a destructive interference, and then by changing the length of these arms, you will start seeing signal. Oops. And that is actually from the video. So yeah, we're shooting the laser. The wave gets split. Gets reflected back, joined, and then notice how here, so far we haven't changed the distance, we haven't changed anything. So initially, you see how peaks, I don't know if you can see in the back, but peaks here are meeting troughs. That is, we're expecting on the screen to see absolutely nothing. And by moving slightly the distances, you see how the pattern changes. And when we see on the screen, sometimes there will be signal, sometimes there wouldn't be. So if we detect some signal, we know that one of those arms must have changed in length. We know that space must have somehow been stretched or squeezed. We know a gravitational wave must have passed by it. So this, however, as you can imagine, is a very, very, very sensitive thing. The smallest perturbation can mess up your experiment. So to be sure that everything worked out, first of all, as I said, there is two LIGOs, one in Washington and one in Louisiana. They're 3,000 kilometers apart, so they're taking data at the same time. So if one of them detects some vibration and the other one doesn't, then we know that that first vibration was some garbage. It wasn't the real signal we were looking for. So each of those arms that you saw on the big picture, each of them is 4 kilometers long. In fact, this is so long that they actually had to level them, because 4 kilometers is so long that the curvature of the Earth started actually mattering. And so they had to level it up, I think, by about a meter vertically to be perfectly leveled. The inside of those tubes are extreme vacuum, because the smallest particles of air, they could interact with your light, and they could scatter the light, and again, your experiment will be a mess. Also, a vacuum doesn't sound vibrations. They need some medium, they need air, and no one can hear you speak in space, because space is a vacuum. So in vacuum, you wouldn't allow any noise being transmitted through the tubes. It is the mirrors. So what we see here is a picture of the inside of one of the mirrors, which is at the bottom. These mirrors are precisely shaped in such a way that they would reflect, and they would keep the laser precisely pointing at the spot we want it to be pointing at. They're very reflective. So when light gets reflected off surfaces, some light sometimes gets, absorbed by the material. However, these are so reflective that 1 in every 3.3 million photons, or 1 in every 3.3 million light particles, actually gets absorbed, and everything else gets reflected. The LIGO's laser is about 200 watts powerful. And also, this system here is it's a somewhat complicated system of 4 pendulums hanging one up over each other and holding the mirror on the bottom to ensure that it's really, 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 really stable. Because if we want to be able to detect 1,000th of the diameter of a proton, we will also be able to detect waves crashing, somebody just riding a bike beside us. So we really need to make sure that this thing is very, very, very stable. So what did LIGO see? So the advanced LIGO, which is an upgraded version of a previous LIGO experiment, was supposed to launch in September 18, 2015. And before every launch of an experiment, we do lots and lots of tests to make sure everything is calibrated, to make sure everything works. And the tests were on one of the test trials that was ending in the early morning of September 14th, around 4 a.m. People were about to shut down the LIGO at the end of the test, but suddenly they have detected some weird noise in space. Well, they detected the noise we were expecting to detect, but basically they detect here what we see is from Washington, Louisiana, what they saw, and here is the 2 signals added, where we have taken into account the difference between them because they're in different places. So what they've noticed, there's a sudden increase in frequency of the signal, something that scientists call a chirp. A chirp? Are you saying there's a giant space bird out there? Not exactly. So a chirp is what we call this sudden increase in frequency is what we call a chirp. It is this characteristic wave signature we're looking for. And if we go back to the simulation and you look on the bottom here, you can see how a red bar just traces down the wave pattern of the different waves. As the 2 black holes are about to merge together, there will be a huge burst in this wave pattern, where the waves will be really stacked really closely to each other in a very high frequency. And basically, this is the chirp we're looking for. Now, why do we call it a chirp? So, just as sound has different frequencies, but when it compresses the air, gravitational waves, when they compress space, they also have different frequencies. Unfortunately, our ear cannot detect these contractions of space. However, scientists saw that the frequency range of that chirp matched actually exactly was within the human hearing range. So you can actually see what a gravitational wave would sound like if we're able to hear the fabric of space-time. And now you're about to hear that exact same. So the chirp is that last thing that you heard at the end. So it sounds kind of like a bird chirping. So what did LIGO actually find? We detected a gravitational wave. Besides that, what do we know? We know that this gravitational wave must have come from two black holes colliding about 1.3 billion light years away. This is really, really, really far. To give you an impression how far it is, our Milky Way is about 100,000 light years in diameter. So this is like 1,000,000 times farther away from our Milky Way. Each of those black holes is about as heavy as 30 suns. And at the end, within 20 milliseconds, people found out that the power emitted by the merger at the end is 50 times more power than if you summed up all the power radiated from all the stars in the observable universe. Which means that within a very short amount of time, a lot of energy was released from that collision. And what you see here is a simulation of what it would have looked like if you were somewhere nearby the black holes at a safe distance. So you see space is being warped around them, and there is also a lensing effect. And as they get closer, this warping becomes stronger and stronger until they merge and it stops. So we didn't actually see that because these things, again, they're 1.3 billion light years away, and black holes are usually way too small to be resolved by our telescopes. So why is this so important, and why am I here talking about it? Well, so first of all, this is the first time we detect gravitational waves. This is also the first time we have observed evidence for black holes that are weighing as heavy as 30 suns. This is the first time we have also observed two black holes rotating around each other. In fact, up until this year, this was just a theoretical thing that people thought it might exist, but we don't actually know if they exist. Also, remember how I said initially that I thought that gravitational waves would be a rare thing? Because initially people thought they would be rare because, how often do you get two black holes colliding together, right? We don't know, but probably not too often. In fact, initially LIGO was expecting to run for at least a year until it discovers something. However, the simple fact that we discovered something as soon as we turned LIGO during a test run means either we got really, really lucky, or those things may be happening more often than we expect. Also, and I think the most important point is that this really opens a new window to the universe. Since the dawn of astronomy, all the information we got from things is by looking at the light, whether that light from the stars, whether that light is visible light, infrared, X-ray, gamma. We always found our information from electromagnetic radiation. However, for the first time this year, we're able to find a source different than light that gives us information about stuff in space. We are finally able to detect the ripples of space-time and how these ripples, they get modified by things being really far away from us. A good analogy about this is to think of it as if for centuries and centuries, astronomers were deaf. We could see, but we were deaf. And suddenly this year, we started hearing. It's like adding a second sense to our toolkit of studying the universe. So it's no surprise that soon enough, people got really excited about this. And at this moment, we have 2 LIGOs in North America, one in Washington, one in Louisiana. There is another gravitational wave observatory in Germany. There is one being built in Italy, the Virgo experiment, one being built in Japan. And India also recently announced that they will join the LIGO collaboration as well. And this is pretty important because the more observatories we have that can detect these signals, the more information we'll be able to collect, and we'll be able to understand better, we'll be able to understand where the source is more precisely on the sky. Another thing we're thinking of is sending a LIGO in space. This project is called ELISA. It is the Evolved Laser Interferometer Space Antenna, and it's supposed to launch in 2034. It has a very similar functioning as LIGO, so it's a huge L, but it's a huge L in space. So instead of 4 kilometers, your arms can now be 1 million kilometers. And you don't have to care about making a vacuum in your tube, because space is already vacuum. Finally, just the way we can split the light in a spectrum for different frequencies, we can also split the gravitational waves in a spectrum. That is, gravitational waves with higher frequencies, they're over here. These are the waves that we can detect with ground-based interferometers, such as LIGO, such as Virgo in Italy. Objects that can be seen with those instruments are black holes merging, neutron stars merging, supernovae. If we go into lower frequency, to detect objects such as, for example, neutron star being swallowed by something called a supermassive black hole, we need to go up in space to detect these things. So ELISA is meant to detect these things. If we go into a lower frequency, we can use something called a pulsar timing array, which unfortunately, we can spend a whole different lecture just about this stuff. But basically, it's using these really cool things called pulsars in space, which act kind of like lighthouses. And by looking at their signal, we can detect whether 2 supermassive black holes, that it's a black hole that is not 30 suns. No. These black holes are as heavy from 1,000 suns all the way to 1 billion, 20 billion suns. These black holes are believed to exist at the center of galaxies. In fact, we know there is one at the center of our Milky Way. And if we go to lower frequencies, we can detect, for example, using cosmic microwave background experiments, we can look for gravitational waves in the very early universe. So finally, I hope I've convinced you why gravitational waves are really cool. And they are very weak, but LIGO was able to detect them. And they really are opening a new chapter in astronomy and physics. And I hope you guys are all really looking forward to the future. Thank you.
Okay, so you saw that Alex did this presentation on a dare, so now it's time to ask him the hard questions. Yeah, you bet.
How do they determine the distance to the merging black holes?
So the question is, how do they determine the distance to the merging black holes? They determine it by studying this frequency pattern that they have detected from the wave. And depending on how far it is, that pattern can give us different information of the distance from it.
So there's can the gravitational waves dissipate? You said energy, right? So the longer they travel, does it eventually dissipate?
So the question is, does a gravitational wave dissipate eventually? That's a good question. So the gravitational waves, they actually, if you are right next to the black hole, they would act differently than if you're next to the solar system far away. And why that is, we'll talk about a little bit about GR. So if we could talk about it afterwards if you want. Yeah, that's a very good question, actually. Yeah.
Gray shirt in the back?
Hey, how is the discovery of the gravitational waves different than, I apologize if I get this wrong, the W map thingy found the cosmic microwave background?
Yes, so the question was about a year ago, this experiment called BICEPS. So if we actually go back, BICEPS is studying this thing called cosmic microwave background, which is the one of the very the first light picture we have of the universe. And they claimed they had detected primordial signature of primordial gravitational waves. First of all, that experiment actually turned out to be not so sure about the results. Turned out that they hadn't taken into account something called dust in space, and that the dust in space actually added some noise to the signal, and that the BICEP experiment was not able to differentiate between the noise and the gravitational wave. However, if they were able to, that would be an indirect observation of gravitational waves. That is, we would be able to detect, once the gravitational wave has passed in the very early universe, the results of it onto the cosmic microwave background. So that would have been an indirect observation, which would have still be cool, but turned out to be not.
Let's say this guy and I are having a bet, and I say, yeah, man, they did discover the cosmic microwave background from the Big Bang. And he's like, no, they didn't. Who wins?
The cosmic microwave background is not from the Big Bang. It's from 100,000 years afterwards.
I see.
Yeah. And we can talk about this after why is that exactly. But maybe another question.
All the way in the back there?
At what speed? Yeah, they propagate at more or less the speed of light to the universe. Yeah.
Yeah, let's suppose that you're standing on a planet, on a star, it happens to be in the same galaxy as this particular event. Is there a position close enough that you would actually feel it physically?
That is actually, so the question was if we're, how close you can get to feel it physically. And that actually goes back a little bit to the question by you when you're talking about whether the wave would dissipate. And that actually is something we could probably talk about afterwards. But basically, the short the short answer is if we get really close to that where the event happens, the physics that we use, the mathematics, the approximations that we use to detect these waves, they're not valid anymore, and it's a bit weirder space-time geometry.
So you wouldn't feel like you suddenly got buzzed or something like that?
It will be something probably more extreme, but I'm not sure. Yeah, yeah.
Yeah, I'm just wondering if LIGO has detected any events subsequent to the first one during its test.
Yeah. So has LIGO detected anything? So LIGO is currently, I'm not sure when they close, but now they're currently closed for upgrades. And they're supposed to relaunch in the fall alongside with Virgo in Italy. So far they haven't declared about anything other besides this discovery, but expect something soon. They expect about 40 discoveries per year, actually, they claim. Yes?
So you mentioned about the possibility of cosmic microwave background polarization.
Mm-hmm.
So if we could somehow filter out between the noise and the dust, would that basically mean that we could theoretically pierce this wall? Like, meaning like as far we can't really see beyond that, would this basically mean that if we could somehow count the dust and remove that dust?
So, yeah. So,
Here past that.
mm-hmm. So the question about the dust in the CMB experiment was that we could see the CMB as it happened 100,000 years ago. 100,000 years after the Big Bang. Why cannot we look backwards? And that doesn't have to do with the dust. It has to do with light just not existing yet.
Because if we could filter out the effects of the dust and see the polarization, basically now go past and see beyond
So if we're able to distinguish the noise between, if we're able to take out the noise from the dust, we should be able to maybe detect indirect evidence for gravitational waves in the very early universe. But we cannot actually look more back in time than the CMB.
So that's still very, we can't really detect.
Yeah, we can't. And why is that? That's a very good question. We could also talk about it after. That's also, yeah.
Okay, we'll get another question. Thought I saw some hands up in the middle. Green shirt.
I just wondered, are there real-world applications for this discovery, like in technology and medicine side?
Yeah. So that's a very good question. Are there any real-world applications for for LIGO? So LIGO, the experiment at LIGO can actually, there already are plans for being used for something else, for seismology. It can detect earthquakes. It's very, very sensible to other stuff. So other fields are looking into applying it as well. For now, it is used mostly for detecting gravitational waves. Now, can the fact that those, now that we have detected these waves, can we get more information into the future about something, about their proposals such as traveling and stuff? Maybe, we don't know. All we know is that there is something that we haven't been able to see up until now, and now we're able to see it, and we're about to discover.
Maybe we'll have one more question if there's any lingering hands. Yeah, you over there?
You said that they propagate at more or less the speed of light? No, they can't propagate more than
Okay. Sorry. Yeah, I meant the speed of light. I just wanted to put a safe blanket around myself.
Okay, thank you all for coming out tonight. I'll get you to thank Alex again in just a moment, but before you do, I'd like to remind you of the feedback forms in your hands. If you're going to do a planetarium show, please hang on to it so you can get it to your planetarium ambassador and let us know how we do with that. Otherwise, we encourage you to fill it out and join us at the front for some cookies. You need to join a planetarium show. We have our two planetarium ambassadors in the back, Heather and Charles. They'll be waiting to meet you in front of the elevators directly across from this room. Thank you all for coming, and let's give Alex a hand.
Thank you.
I didn't actually think you would finish at 10 too, but you did. I'm so pleased.
Yeah.
Thank you.
I really